2, 1, 0. All engine running. Liftoff. We have a liftoff.
Extraordinary responsibility that was on our shoulders to carry out the mission correctly.
Have you ever wondered what the second man on the moon really felt and saw when he stepped onto that silent, dusty world? For decades, Buzz Aldrin kept many of his thoughts guarded, but recent comments have peeled back the curtain. Today, we will walk through his journey, the secrets of the far side, and what those mysteries could mean for the next wave of explorers. If you have ever looked up at the night sky and felt a chill of curiosity, this story is for you. In the late 1950s, the United States and the Soviet Union were locked in a race that leaped beyond political borders. When the Soviet satellite Sputnik beeped across the radio on October 4th, 1957, it felt like an alarm bell for the West. Less than 4 years later, Yuri Gagarin orbited Earth, proving that people could survive in space. The challenge was clear, and President John F. Kennedy answered by setting a breathtaking goal: land an American on the moon and return him safely before the end of the decade. That goal ignited the Apollo program. Factories spun up overnight, engineers slept under drafting tables, astronauts trained until their muscles ached. It was more than pride. It was an extraordinary responsibility carried on very human shoulders. One of those shoulders belonged to Edwin Eugene Aldrin Jr., known to the world as Buzz. Born in 1930 in New Jersey, Buzz graduated third in his West Point class. He fought MiG-15s over Korea, flew more than 60 combat missions, and later earned a doctorate in astronautics at MIT, writing about how spacecraft could rendezvous in orbit. That knowledge would soon be used for real. When NASA began choosing astronauts, they first wanted only test pilots, but the rules changed just in time for Aldrin and his 2,000-plus hours in jets. In October 1963, he became part of Astronaut Group 3, and 3 years later on Gemini 12, he set records for spacewalking and docking. Still, nothing compared to the mission designated AS-506, Apollo 11. On July 16, 1969, more than 25 million Americans watched their televisions as the Saturn V thundered into the blue. Its 3 stages hurled Neil Armstrong, Michael Collins, and Buzz Aldrin toward a new chapter in human history. 3 days later, the service module slipped behind the moon and fired its engine to enter orbit. The crew studied the Sea of Tranquility, looking for a smooth field among craters that could hide boulders as large as buses. Early on July 20th, the lunar module Eagle undocked. Inside its cramped cabin, Armstrong took the commander's left seat. Aldrin read out velocity, range, and descent rate from the right. Alarms blared when the guidance computer overloaded, but they pressed on. With only seconds of fuel left, Armstrong took manual control and settled onto a patch of dust and scattered rocks. Houston, Tranquility Base here. The Eagle has landed. After checks and a short rest, Armstrong climbed down the ladder and spoke his famous line. 19 minutes later, Aldrin followed. His first words were simple: beautiful view. Then, turning poetic, he called the scene a magnificent desolation. The phrase still echoes in museums and documentaries, and it hints that Aldrin saw more than a field of gray powder. While on the surface, the 2 astronauts planted a flag, placed scientific gear, and collected rock samples. Aldrin, a Presbyterian elder, even took a brief moment for silent communion, the first religious ceremony on another world. But time was short. After about 2.5 hours outside, they climbed back inside Eagle, slept, and blasted off to rejoin Collins. The public side of the story ends with a splashdown in the Pacific on July 24th. But Aldrin's private reflections stretch far longer. Friends say he wrestled with the experience, the loneliness of space, the vision of Earth 238,000 miles away, and the silent backside of the moon that no human eye had seen until a few months earlier during Apollo 8. What did that hidden hemisphere look like up close? Scarred, jagged, almost alien compared to the near side with its familiar dark seas. The far side's surface bakes at 127 degrees Celsius during the long lunar day and plummets to minus 173 at night. Without an atmosphere, the heat swings are brutal. The land is packed with craters stacked on older craters, and in the south lies the gigantic South Pole Aitken Basin, one of the largest impact scars in the solar system. Imagine standing on the rim of a dent the size of India, frozen in time for billions of years. During his orbits, Aldrin looked down and felt both wonder and duty. For many years, the far side was called the dark side, not because it lacked sunlight, but because radio contact with Earth was impossible when spacecraft slipped behind the lunar globe. Modern probes solved that with relay satellites, yet the nickname stuck, adding a layer of mystery that still fuels books and rock albums. Aldrin has hinted that what surprised him most was not a UFO or alien structure, but the sheer possibility. He realized that an outpost could hide there, shielded from Earth's noisy radio chatter, perfect for giant radio telescopes listening to whispers from the early universe. The moon, he decided, was not an endpoint, it was a doorway. Scientists today agree. The far side offers a radio quiet zone, deposits of helium-3 for potential fusion reactors, and thorium concentrations like the Compton-Belkovich anomaly that could become a nuclear fuel pantry. The soil, or regolith, is rich in oxygen bound inside minerals. Future settlers could extract it for breathing air and rocket oxidizer. Water ice hides in polar craters, waiting to be melted into drinkable water or split into hydrogen and oxygen for propellant. Aldrin's magnificent desolation might one day power shining cities. Of course, reality is tougher than dreams. Any base must survive razor-sharp lunar dust, micrometeorites, and month-long nights. Machinery has to endure repeated cycles of oven heat and deep freeze. Solar storms can saturate electronics and threaten human health. But engineers are already tackling those problems. Inflatable habitats with regolith shielding, nuclear surface power plants, and autonomous robots that build landing pads from molten soil are being tested today. Buzz Aldrin retired from NASA in 1971, yet he never stopped pushing. He proposed the Aldrin Cycler, an orbit that swings continuously between Earth and Mars, reducing fuel demands for crewed missions. He urged Congress to think of the moon as a training ground and Mars as the horizon goal. When asked why he was so focused on moving outward, he answered, "Exploration is wired into our souls." Recent missions prove the momentum is back. China's Chang'e 4 made history in 2019 by soft landing on the far side and deploying the Yutu-2 rover. It mapped underground layers and found hints of mantle material. In 2023, India's Chandrayaan-3 touched down near the South Pole, discovering sulfur and recording the first local moonquake. Private companies from the United States to Japan are experimenting with landers, drills, and rovers that can hitch rides on commercial rockets. NASA's Artemis program plans to return astronauts to the surface soon, using a small lunar space station called Gateway as a relay. Every success traces back to Apollo 11's footprint trails and to the unspoken observations Aldrin carried home. He has said that when he stared at the barren horizon, he also saw Earthrise in his mind, a blue marble covered with thin clouds and even thinner ideas of division. The moon showed him how fragile home really is. What would Buzz Aldrin tell a new astronaut preparing for the far side? Probably this: respect the unknown, keep learning, share what you discover, and remember you are part of a chain that began long before you and will continue long after. The moon keeps no secrets forever. Its rocks preserve ancient impacts, its frozen craters hold records of water delivery, and its vantage point lets telescopes search for life around distant suns. The more we study it, the more we understand ourselves. Think about that the next time you glimpse the moon riding high above city lights. Somewhere on that sphere is a silent imprint of a boot. Nearby are sensors still reflecting laser beams back to Earth, allowing students to measure the moon's gradual drift away from us, about 3.8 centimeters per year. The science continues half a century after the cameras turned off. And so does the wonder. Children who watched Apollo 11 grew up to invent smartphones, 3D printing, and reusable rockets. The next generation may watch construction crews assemble habitat domes on live video feeds. Maybe you will be one of them. Maybe you will operate a telescope that catches the first signal from a planet circling a faraway star, all because a radio-quiet site on the far side lets you listen. Buzz Aldrin's recent openness offers a reminder. History is alive. The stories we tell shape the missions we dare to fly. By recounting the challenges, the eerie silence, and the dazzling possibilities, Aldrin passes the torch. It now rests in our hands. So what comes next? Robotic scouts will map safe routes across permanently shadowed valleys. Rovers will drill into crusts looking for metals and water ice. Inflatable greenhouses will test crops under low gravity. And one day a human crew will land on the far side, perhaps near the South Pole Aitken Basin, step out, and find themselves standing inside a new chapter of the same grand book. When that happens, a small part of their courage will trace back to a man who once called the moon magnificent desolation, then urged us all to go back. We owe it to Buzz Aldrin and to ourselves to keep walking. Back on Earth, Aldrin's return was joyful in public but stormy in private. The sudden fame felt heavy. Reporters wanted sound bites, politicians wanted handshakes, children wanted autographs, yet few people asked how the voyage had changed him inside. In later interviews, he admitted to bouts of melancholy, periods when ordinary life seemed small after gazing at the entirety of Earth through a tiny window. He worked through those struggles, spoke openly about mental health, and encouraged fellow veterans to seek help when shadows grew long. For years, Aldrin seldom discussed what he noticed on the surface beyond the official mission logs. Recently, during university talks and podcasts, he began to describe little moments that photographs cannot capture. The smell of burnt gunpowder that clung to his suit after he repressurized the cabin. The way lunar dust floated like smoke in weightlessness. The electric thrill when the seismometer first pinged a reading through his earpiece. Listeners leaned forward, realizing that the real treasure of exploration is often hidden in sensory fragments and quiet reflections. Why does the far side matter so much? First, science. Radio waves that never reach Earth can be captured there, letting us listen to the dawn of the universe. Second, resources. Helium-3 in the soil could power clean fusion, and polar ice can become water and fuel. Finally, settlement. A permanent outpost would prove that humanity can thrive off-world the same way railroads once opened new frontiers. Thorium adds a second energy option. Reactors that breed uranium-233 from thorium can be passively safe and produce only small amounts of long-lived waste. The Compton-Belkovich anomaly is rich enough that some scientists joke about calling it Moon Harbor. Setting up a thorium test reactor there would offer constant sunlight near the poles for solar backup and vacuum conditions that help certain types of metallurgy. Even if the first results are modest, each experiment builds knowledge that can be applied in harsher places like Mars or the moons of Jupiter. Technology is rushing ahead too. NASA's Space Launch System and Orion capsule have already flown around the moon without crew. SpaceX is testing the huge Starship vehicle that could deliver over 100 metric tons of cargo per launch, enough to carry a complete base module in one shot. Blue Origin, the company founded by Jeff Bezos, plans a lunar lander called Blue Moon. Smaller firms are building autonomous drills, solar farms that unfold like origami, and 3D printers that use microwave beams to melt dust into bricks. While hardware improves, so does planning. Scientists now create high-resolution maps from laser altimeters and radar soundings. They simulate dust storms, thermal gradients, and radiation bursts to test habitat designs on Earth. One clever idea is to bury inflatable living quarters in trenches, then cover them with half a meter of regolith. That shield would cut radiation exposure to near-Earth levels and keep temperatures stable. Another concept uses mirror farms on crater rims to bounce sunlight into permanently shadowed ice deposits, turning them into gleaming lakes of fuel. Yet danger remains. The moon's gravity is only 1/6 of Earth's, and muscle loss can weaken explorers in weeks. Engineers examine rotating habitats or suit-based resistance systems to keep bones strong. Lunar dust, charged by solar ultraviolet light, clings to everything and can slice into seals and lungs. Future suits may have electrostatic fields that shake particles off before astronauts re-enter airlocks. Constant vigilance, Aldrin warns, will be as vital as courage. Culture will evolve too. Imagine students producing ceramics from local clay, artists mixing lunar glass into sculptures, or chefs experimenting with plants grown under LED lamps powered by thorium reactors. Each success will generate stories, songs, and idioms unique to an off-Earth life. Aldrin once said that planting the first boot prints was only the opening scene. The real saga begins when families celebrate birthdays under 2-week sunrises. All of these paths, science, energy, diplomacy, technology, culture, loop back to a fundamental human drive. We explore to understand who we are. From cave paintings to sea voyages to particle accelerators, curiosity acts like gravity on the mind, pulling us outward. Buzz Aldrin embodies that impulse. His recent recollections are not just nostalgic tales. They are bridge posts between what has been done and what can still be done. In practical terms, the next decade should see the first sustainable presence at one of the lunar poles. Solar fields will send power to cryogenic plants that turn ice into water and fuel. Rovers will scout lava tubes as potential shelter. Astronaut crews may rotate every 6 months, using lessons in radiation management, closed-loop life support, and psychological resilience that will later be essential for Mars. Each milestone will owe a nod to the blueprint sketched by Apollo, but written with 21st century ink. The voice of an elder explorer carries weight in these discussions. When Aldrin tells policymakers that staying in low Earth orbit is like camping in the backyard, they listen. When he points out that children born this year could see a human fly past Saturn, parents realize that long-term vision matters. He challenges us to aim not for flags and footprints alone, but for lasting settlements whose value outlives political cycles. Will we meet that challenge? The answer depends on everyday choices: funding for science classes, support for mental health among astronauts, respect for international agreements, and courage to pursue breakthrough technologies like helium-3 fusion. Aldrin's revelations add urgency. They remind us that the moon remains more foreign than familiar, that half of it was unseen by any human until the middle of the 20th century, and that the rest still holds secrets deep beneath its dusty crust. Before we end, here's a thought experiment. Picture yourself in a small habitat module on the far side. Outside, the regolith is pale silver in the sun. You flip a switch and the lights of a radio dish power up, listening to cosmic murmurs 13 billion years old. On your screen, Earth is a thin crescent, blue and delicate. Communication lag is only a couple of seconds, yet the psychological gulf feels wider. In that moment, you understand the same truth Aldrin felt. Exploration shrinks the universe but expands the soul. As you zip up your suit for a moonwalk, maybe you will recall the words "magnificent desolation" and add your own line, because every explorer authors a piece of the narrative. Perhaps you will describe a sky where stars never twinkle, or the way dust mutes footsteps in vacuum. Then you will speak into your microphone, and some child on Earth will hear you and dream bigger. That circle of inspiration is why Buzz Aldrin's story still matters. It is why we made this video. By unpacking his memories, we gain clues about how to build our future. With each revelation, we step closer to a time when the question is no longer, should we go? But how soon can we launch? Thank you for joining this journey. If this video sparked your curiosity, share it with a friend, subscribe for more stories of exploration, and keep looking up. The sky is not the limit. It is only the beginning. Always keep dreaming and keep reaching for the stars and beyond.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. Now, it takes many billions of years to create a galaxy, like the Milky Way galaxy, with 100 billion stars, many billions of years old.
Imagine looking up at the night sky and discovering something so strange, it turns science on its head. That is exactly what happened when the James Webb Space Telescope spotted 6 massive, ancient galaxies that should not be there. Today, we are going to travel back in time with Webb, peek at these cosmic rebels, and ask why their very existence is rewriting the story of the universe. The James Webb Space Telescope, or JWST, is the largest and coldest eye humans have ever sent into space. Its gold-covered mirror is as wide as a small house, and it unfolds like a flower after launch. Webb sees heat instead of ordinary light, so it can look through dusty clouds and reach back billions of years, because old light from the early universe has stretched into gentle infrared waves while crossing the expanding cosmos. When scientists aimed Webb at a tiny, dark patch of sky, they expected to find small baby galaxies. Instead, the telescope sent back images filled with bright red dots. Those dots turned out to be galaxies that were already huge when the universe was only a few 100 million years old. According to the usual math, there simply was not enough time or material for them to grow so fast. It was like opening a history book about ancient villages and finding photographs of skyscrapers. To understand why Webb can make such discoveries, let us explore its four main tools. First is a NIRCam, a near-infrared camera that takes sharp pictures of distant objects. Next comes NIRSpec, a spectrograph that splits light into rainbows so scientists can read the chemical fingerprints of stars and gas. The third is MIRI, which sees mid-infrared light and can spot cool dust where new stars are born. Finally, Webb carries a fine guidance sensor that keeps the telescope locked on target, plus a small slitless spectrograph for quick surveys. But what exactly did Webb find? Let us meet the 6 troublemakers that astronomers jokingly call universe breakers. The first galaxy, nicknamed GN-Z11, shines from more than 13 billion light-years away. It is compact, about the width of our Milky Way, yet it already holds enough stars to outweigh the Milky Way many times over. Seeing so much mass packed so early makes researchers wonder if star-making was turbocharged in the young cosmos. Galaxy number 2, GN-Z10, is even brighter than theory says is possible. Its glow hints at a storm of newborn stars popping into life at once. If that is true, then the recipe for building stars must have been far more efficient than anyone thought. The third, GN-Z9, surprises scientists with heavy elements such as carbon, oxygen, and nitrogen. Those elements form inside massive stars and are scattered by supernova blasts. Finding them so soon after the Big Bang means many big stars must have already lived, died, and seeded space with the raw material for planets and eventually life. Galaxy 4, GN-Z8, shows a graceful rotating disk. Disks are fragile. They need calm conditions to settle, yet the early universe was a violent place full of collisions. Seeing a tidy disk so early suggests galaxies could organize themselves much faster than simulations predict. The fifth galaxy, GN-Z7, is loaded with dust. Dust grains are the bricks that build rocky worlds. Their presence hints that planet-forming cycles may have started long before our own solar system existed. The last member of the set, GN-Z6, has an odd redshift that makes it look as if the space around it is expanding a little more slowly than average. If this reading holds up, it could reveal wrinkles in the large-scale fabric of the cosmos and offer clues about dark energy. All of these discoveries raise big questions. How did so many stars gather so quickly? Did the first stars behave differently from the ones we see today? Could some of these red dots hide giant black holes that swallow light and puff up their host galaxies? Every answer could shake or strengthen the foundations of modern cosmology. One explanation is that early gas clouds cooled and collapsed faster than expected, feeding a frenzy of star birth. Another idea is that the first stars were far more massive than modern stars. They would burn fiercely, live briefly, and explode, spreading heavy elements in record time. A third possibility is that our computer models miss some piece of physics about dark matter, the invisible glue that feeds galaxy growth. To test these theories, astronomers need more data, and that is where Webb's spectrographs shine. By spreading each galaxy's light into thin stripes, scientists measure its distance, age, and chemical recipe with high precision. Those spectra act like cosmic barcodes, telling us exactly how old the starlight is and what elements forge inside those suns. The shock of these early giants also affects the future of space missions. Telescopes on the way, such as the Euclid satellite and the Vera Rubin Observatory, will map the shapes and motions of billions of galaxies. Their surveys can check how common these heavyweights really are. If they turn out to be everywhere, textbooks on galaxy formation will need a full rewrite. Discovering early dust and heavy elements also fuels the hunt for life. If ancient galaxies made planets quickly, maybe some worlds had enough time to brew simple life long before Earth existed. Upcoming missions that search for exoplanet atmospheres could look for biosignatures in unexpected corners of the sky. On the theoretical side, the findings force cosmologists to tweak their models of dark matter and dark energy. Dark matter halos might have gathered mass sooner than believed, dragging gas into deep wells where stars could ignite. Dark energy, which accelerates cosmic expansion, may not behave exactly the same everywhere. Webb's odd redshifts could help trace such subtle differences. Yet some mysteries might demand even bolder ideas. Perhaps gravity acted differently under the extreme conditions of the infant universe. Or maybe exotic particles played a brief but crucial role in cooling gas. For now, scientists keep their minds open. While new instruments arrive, Webb will continue its watch. Each time it stares at a blank field, it peels away another layer of history. Its images remind us that the universe still holds surprises no matter how many equations we write. Let us take a step back and think about the journey from the first spark of the Big Bang to the rich tapestry of galaxies we see today. In that first instant, space was smaller than an atom. As it expanded and cooled, simple hydrogen and helium formed. Gravity gathered those atoms into clouds. Inside the densest knots, the first stars switched on, flooding space with light and carving out bubbles in the fog of gas. Those stars lived fast, died young, and set the stage for galaxies. Fast forward a few 100 million years, and the 6 galaxies Webb just saw are already shining. Their light travels through the swelling universe, stretching into infrared waves. Finally, more than 13 billion years later, that faint glow reaches Webb's mirror and triggers its gold detectors. In that moment, our species gets to witness a snapshot of creation itself. This story is about more than numbers and theories. It shows how curiosity fuels progress. Teams of engineers spent decades designing every screw on Webb. Scientists learned how to guide a telescope the size of a tennis court to a point 4 times farther than the moon. Nations cooperated, budgets grew, setbacks happened, but the dream stayed alive. And the reward is a picture that forces us to rethink everything we thought we knew. So what comes next? First, researchers will confirm the distances to these galaxies with deeper spectra. Then they will peer inside them to see if baby black holes lurk at their cores. They will also search for similar objects in other fields to check if the find was luck or a common trend. Meanwhile, computer teams will run new simulations, tweaking star formation rules to match the unexpected data. Students entering astronomy today will write their theses on puzzles that did not exist a year ago. That is the beauty of science. Each answer opens 10 new questions. As we refine our models, we edge closer to understanding how something came from nothing and how that something grew into galaxies, stars, planets, and us. Before we close, think about this simple fact. The light that built these images left its source when our universe was less than 1 billion years old. Back then, Earth, the Sun, and even the Milky Way were still far in the future. Yet that ancient light traveled patiently through the vast dark until a fragile mirror in space caught it. In a sense, the universe kept a diary for billions of years and just handed us the newest pages. We do not yet know whether these 6 galaxies will stand as true record breakers or if follow-up studies will reveal a more ordinary story. Either outcome teaches us something vital. If the galaxies are as massive as they look, then nature has tricks we need to learn. If they turn out to be smaller or closer than first thought, that means our tools and methods improve so quickly that we caught the error within months. Both scenarios show science working as it should, and that is why the discovery matters. It is not only about distant worlds, it is about asking bold questions, testing ideas, and accepting whatever the universe tells us. Before we dive deeper into the mystery of these galaxies, let us pause to picture how Webb reaches such faraway scenes. The telescope orbits the Sun around a spot called Lagrange Point 2, or simply L2, about 1.5 million kilometers beyond Earth on a line straight out from the Sun. At L2, Earth and Sun's gravity balance in a way that lets Webb circle quietly while always keeping Earth, Moon, and Sun on the same side, allowing Webb's giant shield to block harmful heat and light. Because Webb observes in heat waves, it can even see through galaxies that act as natural magnifying glasses. This trick is called gravitational lensing. Einstein's theory of relativity tells us that mass bends space, and when light passes near a massive object like a galaxy cluster, its path curves. If the alignment is just right, light from a hidden background galaxy can be stretched and brightened into an arc or ring, letting Webb peek even further back in time. Now, you might ask how astronomers decide that a blurry red dot is truly ancient. They measure redshift, the amount by which the wavelength of light has stretched. The bigger the redshift, the farther the light has traveled and the older the object. For most of the past decade, redshifts above 10 were rare. Webb is routinely finding objects around redshift 13 and beyond. The 6 galaxies in today's story sit in that zone, meaning their light left them when the universe was less than 5% its current age. Redshift is measured with spectra, but Webb's cameras first spot candidates. NearCam captures deep images through several color filters. Scientists compare the brightness in each filter and look for a sudden drop between 2 colors. That drop signals that ultraviolet light from young stars has been stretched beyond visible red into the infrared. This Lyman break method helped pick out our 6 unusual galaxies. Once a candidate is flagged, our spec moves in. It can take spectra of hundreds of objects at once thanks to tiny doors called micro-shutters that open and close like pixels on a screen. Each shutter is the width of a human hair. Computer algorithms decide which shutters open so that light from each galaxy passes through while the sky around stays dark. The result is a pattern of stripes that reveals distances, temperatures, and chemical makeup. Let us return to the conundrum of mass. Building a galaxy as heavy as the Milky Way requires lots of gas turning into stars. In the nearby universe, that process takes billions of years. Seeing similar mass achieved in only 500 million years suggests that early gas clouds were denser, cooler, or subject to stronger flows of dark matter. New theories propose direct collapse black holes or other exotic processes to explain such rapid growth. Computer simulations try to recreate such scenarios. Programs like Illustris, Eagle, and Fire divide the universe into 3-dimensional grids, track billions of particles of gas and dark matter, and let gravity sculpt them. The latest runs incorporate feedback from supernovae and black holes, but none predicted a crowd of giant galaxies so early. Modelers are now tuning energy outputs, initial gas temperatures, and the mix of dark matter to see if they can match Webb's images without breaking other observations. While astronomers puzzle over theory, engineers are planning future explorers. The Nancy Grace Roman Space Telescope will carry a mirror almost as large as Hubble's, but with a view 100 times wider. Roman will scan the sky for supernovae, measure dark energy, and, paired with Webb, examine early galaxy clusters in detail. Europe's Euclid mission will chart billions of galaxies to trace dark matter webs stretching across the heavens. On the ground, the Vera Rubin Observatory will take a picture of the entire visible sky every few nights, catching transient events and building deep maps over a decade. Each of these projects relies on lessons learned from Webb. They will share data, cross-calibrate distances, and work like detectives, swapping clues. In this cooperative spirit, the scientific community hopes to solve the mystery of how the first massive galaxies came to be. Let us zoom in on the role of supermassive black holes. In the heart of almost every nearby galaxy, including our Milky Way, lurks a black hole millions to billions of times the sun's mass. Astronomers think these giants grew over time by swallowing stars and gas and by merging with other black holes. But if some early galaxies housed black holes even half as massive, those holes must have started enormous. One proposal suggests that huge gas clouds collapsed directly into black holes without first forming stars, an idea Webb's data now puts to the test. The presence of dust in GNZ 7 brings chemistry into focus. Dust forms in the winds of dying stars and in supernova blasts. It is made of carbon, silicon, iron, and more. Dust grains stick together to create pebbles, rocks, and eventually planets. If dust existed only a few 100 million years after the Big Bang, then the seeds of planetary systems appeared remarkably early. By studying dust emission with MIRI, Webb can estimate grain sizes and temperatures, building a timeline from first stars to first planets. Some people might wonder how discovering old galaxies affects everyday life. The answer lies in technology and perspective. Building Webb required ultra-light materials, cryogenic electronics, and foldable structures. These advances feed back into medical imaging, climate satellites, and even consumer cameras. Beyond hardware, cosmic discoveries remind us that our Earth is part of a larger story. Knowing that stars created the calcium in our bones and the iron in our blood connects us to the universe in a personal way. Education also gains from this sense of wonder. Teachers use Webb images to spark interest in science, technology, engineering, and math. Students learn how a question about distant galaxies involves physics, chemistry, computer science, and international teamwork. This holistic approach prepares the next generation to tackle global challenges. While Webb headlines capture attention, ground-based telescopes complement its findings. Giant mirrors like those on the Keck Observatory and the Very Large Telescope can zoom in on specific targets highlighted by Webb, taking high-resolution spectra in visible light. Soon the 30-meter telescope and the extremely large telescope will join the hunt, offering sharper views from Earth than ever before. Another exciting tool is ALMA, the Atacama Large Millimeter/Millimeter Array. It detects coal, gas, and dust whose radio waves paint a different picture from Webb's infrared view. By combining their data, astronomers can map both the hot star-forming regions and the cold reservoirs that fuel them, building a complete picture of galaxy growth. Public interest plays an essential role too. Each striking Webb image reaches millions on social media, prompting discussions about space, science funding, and humanity's future. When citizens see direct returns on their investment, they are more likely to support ambitious missions that push the boundaries of knowledge. Let us imagine standing on a rocky planet inside one of the 6 early galaxies. The night sky would look different. Other galaxies would be closer, larger, and brighter, glowing with massive young stars. Supernovae would light up the darkness like sudden fireworks. Heavy elements would be scarce, and planets might lack thick atmospheres. Yet, even in such a raw environment, chemistry could lay the groundwork for life. If life emerged there and survived until now, it would be unimaginably ancient and perhaps unrecognizable. The philosophical implications are profound. We like to think of time as an arrow, moving from simple to complex. But Webb shows that complexity arrived quickly. That challenges our assumptions about inevitability. Maybe life too can spring up faster than we thought. Or maybe the early universe was too harsh and complexity had to wait. Each discovery shapes our understanding of our own origins. Science fiction writers are already weaving these revelations into stories. Tales of primeval civilizations, of black holes birthing galaxies, of universal constants changing over time, all draw inspiration from real data. Artistic expression, fueled by scientific fact, enriches our culture and helps more people engage with abstract ideas. In the coming years, Webb will also study exoplanet atmospheres by watching planets pass in front of their stars. The same detectors that catch ancient galaxies can measure how starlight filters through alien skies, revealing water vapor, methane, or even possible signs of life. Thus, the quest that starts at the edge of the universe loops back to the search for neighbors in our own galaxy. Throughout history, each new telescope revolutionized astronomy. Galileo's spyglass showed moons around Jupiter. Hubble revealed expanding space. Now Webb displays galaxies that should not exist. In a few decades, a successor might image the first tiny sparks after the Big Bang itself, or map surfaces of Earth-like exoplanets. Our story with the stars is far from finished. Let us recap the main points. Webb detected 6 massive galaxies when the universe was only a few hundred million years old. These objects challenge current models because they are too big, too dusty, and too chemically evolved for their age. Possible explanations include ultra-fast star formation, direct collapsed black holes, or new physics in dark matter and dark energy. Future missions and ground-based observatories will gather more data to solve the puzzle. Above all, this discovery reminds us that the universe is an active laboratory, always ready to surprise. Every observation is a conversation with nature, and sometimes nature answers with a twist we never expected. In the spirit of curiosity, keep following the journey of the James Webb Space Telescope and the scientists who read its messages. The cosmos has many more stories, and together we will keep turning the pages. Stay curious and join us for more cosmic journeys ahead.
Leading New Zealand scientists have designed a credible scenario for an earthquake and tsunami on the Hikurangi subduction zone.
Imagine standing on a quiet beach in New Zealand. The air smells of salt and wildflowers while gentle waves fold onto the sand. A gull cries overhead, and everything feels steady. Then the ground begins to hum. The vibration grows louder until the shore itself shudders like a living drum. This picture is no fantasy. On March 25th, 2025, a magnitude 6.8 earthquake rocked the South Island. Windows rattled, cupboards sprang open, and pets dashed for cover. Although serious damage was rare, the jolt delivered a clear warning. New Zealand sits on a restless seam between 2 giant tectonic plates. Any day, a far larger quake could arrive, changing towns, coastlines, and lives in a single violent afternoon. In this video, we will explore what happened in March, why it matters, and how science shows an even bigger event may be waiting in the wings. By the end, you will know the risks, the signs, and the simple steps that can keep you and your community ready when the ground decides to move again. The recent earthquake. The March quake struck at 2:43 in the afternoon, a busy time when schools were packing up and offices were finishing lunch. Seismometers placed around the nation showed the epicenter about 159 kilometers southwest of Riverton, deep in the ocean near the edge of the Pusagar Trench. Because the rupture lay only 10 kilometers below the seabed, the shaking raced quickly to the surface. More than 4,700 people filed sensation reports with GeoNet within the first hour. Some felt only a soft roll, while others described sharp vertical jolts that knocked books from shelves. Trains on the South Island halted automatically to avoid derailment. Coastal emergency managers broadcast precautionary messages telling boaters to leave the water and walkers to step back from piers. Thankfully, no tsunami formed, and engineers later confirmed that bridges, power cables, and water pipes remained sound. Still, the psychological impact ran deep. In Christchurch, memories of the tragic 2011 quake resurfaced, and counseling hotlines lit up with calls. The nation breathed a collective sigh of relief, but scientists instantly turned the event into data, eager to learn what secrets it held about the faults below. Why the quake matters. At first glance, a magnitude 6.8 earthquake may seem moderate compared with monster quakes in Japan or Chile, yet its real value lies in what it reveals. Think of the plate boundary like a giant wooden beam slowly bent by two opposing forces. Tiny cracks appear long before the beam snaps. Each moderate quake is one of those cracks, showing where stress is highest and how energy travels through the crust. The March tremor highlighted renewed activity near the Pusagar Trench, a sector already known for large releases in 1970, 2003, and 2009. Patterns in aftershock locations suggest fresh fractures along connecting faults that feed stress toward the Alpine Fault to the northeast. For researchers, every waveform recorded, every centimeter of seafloor displacement measured, feeds computer models that estimate future rupture sizes. The event also reminded policymakers that preparedness budgets cannot rest. School drills, hospital backup systems, and public alert networks all rely on consistent funding. In short, this single quake reopened national conversation about the bigger one. Experts fear is overdue. New Zealand's restless ground. New Zealand stretches across the collision zone between the Pacific Plate and the Australian Plate. North of Wellington, the Pacific Plate dives beneath its neighbor along the Hikurangi subduction zone, dragging the seafloor down like a slow conveyor. South of Fiordland, the roles reverse. The Australian Plate sinks under the Pacific Plate along the Pusagar Trench. Linking these two huge dives is the Alpine Fault, a nearly 800-kilometer tear that slashes the spine of the South Island. This complex boundary makes the country one of the most seismically active places on Earth. Over 15,000 quakes shake the islands each year, though most are too weak to notice. The same forces that lift the Southern Alps into sky-piercing peaks also twist cities and crack highways. For geologists, New Zealand is a living laboratory. For residents, it is a beautiful home that must always be treated with caution and respect. What is a megaquake? Scientists call any earthquake of magnitude 8.0 or higher a megaquake. The energy difference between magnitudes might sound small on paper, but the scale is logarithmic. Each full step releases around 32 times more energy. A magnitude 6.8, like the recent event, rattles dishes. A magnitude 8.8 can move mountains. Megaquakes usually happen where one tectonic plate plunges beneath another, because subduction zones allow faults to lock over vast areas, storing centuries of strain. When the lock finally breaks, the seafloor can lurch upward by several meters, pushing up a huge dome of water that becomes a tsunami. Rupture lengths can exceed 1,000 kilometers, and shaking can last 5 minutes or more. The 2004 Indian Ocean quake and the 2011 Tohoku quake are stark examples. New Zealand hosts 2 subduction zones and 1 giant transform fault, giving it all the ingredients for a future megaquake. The Alpine Fault. The Alpine Fault takes up most of the sideways motion between the plates in the South Island, sliding at roughly 30 millimeters each year. Trench studies of river sediments show evidence of at least 27 major ruptures over the past 8,000 years, with an average repeat time of about 3 centuries. The last full-length rupture struck in 1717, well before European settlers arrived. Indigenous oral history records, landslides, and landscape changes from that event, By statistical chance alone, another break is likely in the coming decades. When it goes, scientists expect up to 2 minutes of intense shaking across the entire island, followed by thousands of aftershocks. Ground offsets along the fault could reach 8 meters in places, slicing roads and pipelines instantly. Modern building codes will help newer structures, but many historic stone buildings may not survive. Emergency planners call an alpine fault rupture the most predictable large disaster in the country, because the geological clock is clearly ticking. The Puisager Trench. Farther southwest, hidden beneath dark ocean swells, lurks the Puisager subduction zone. Here the Australian plate sinks under at roughly 35 millimeters per year. The trench is remote and rough, whipped by roaring 40s winds that hammer research ships. As a result, fewer sensors cover this zone compared with its northern cousin. Still, the record shows repeated magnitude 7+ events in recent decades. A full margin rupture could exceed magnitude 8.5. Because the break would start offshore, shaking on land might be slightly less severe than an alpine fault quake, yet the tsunami risk would be higher. Fjord communities like Milford Sound sit at the end of long, narrow inlets that could funnel waves to dangerous heights. Tourist boats, tiny airstrips, and single-lane highways in the region all face unique evacuation challenges. Improving seabed monitoring in the trench is a priority for international science teams, but harsh weather means progress is slow. Tsunami threats. Tsunamis are often imagined as distant source waves that give hours of notice, but local sources are different. In a local megaquake, the first warning is the quake itself. If shaking lasts longer than 1 minute or is so strong that standing is hard, coastal residents must move inland or uphill immediately. Sirens and text alerts may follow, but self-evacuation buys the vital minutes. Computer models show that a Puisager megaquake could deliver waves to the South Island's west coast in 10 to 15 minutes. A Hikurangi event could slam the east coast of the North Island just as quickly. Wave heights vary with the shape of the seabed. Bays may see amplifications that turn a 2-meter offshore wave into a 5-meter wall at the shore. Beyond the first crest, dangerous currents can last many hours, snapping moorings and dragging debris back out to sea. Rebuilding after a tsunami often takes longer than repairing earthquake damage because salt water contaminates soil and infrastructure. What a megaquake could do. Imagine State Highway 1 south of Kaikoura twisted into jagged ridges, with fallen cliffs blocking both ends. Picture the main rail line broken in dozens of places, leaving freight wagons stranded. Landslides in the southern Alps could dam rivers, forming lakes that later burst in flood valleys. In Christchurch, soft soils might liquefy again, tilting houses and swallowing footpaths. Wellington's steep suburbs could see retaining walls collapse onto roads, isolating hill communities. Power grids would face simultaneous failures, snapped poles in rural areas, and damaged transformers in urban substations. Cell towers might stay up, but the fiber cables feeding them could break, cutting voice service for days. Ports could lose cranes, slowing the flow of fuel and food. All these impacts compound. Supermarkets run low, petrol stations ration, and hospitals depend on backup generators. The national economy could shrink by tens of billions of dollars in a single year, and recovery would stretch across the next decade. Can we predict it? Despite advances in Earth science, precise earthquake prediction remains beyond reach. Researchers can map which faults are most likely to break and calculate probabilities over decades, but they cannot yet say next Tuesday at noon. The best estimate for the Alpine Fault is a 75% chance of a rupture in the next 50 years. For the Hikurangi margin, large event probability sits around 20% in the same period. These numbers guide insurance rates and building codes. They also remind citizens that low probability is not zero. Volcanoes and cyclones offer visible clouds or smoke before they strike. Earthquakes give no such early sign, so preparation must rely on statistics, not instincts. Scientists continue to test ideas like subtle gas emissions, radon spikes, or animal behavior as short-term clues, but results are inconsistent. For now, the safest posture is permanent readiness. Early warning in science. Early warning systems work by detecting the first fast P waves that radiate from a rupture. These waves shake little but travel quickly. Computers in the network calculate location and magnitude within seconds and send alerts ahead of the slower, destructive S waves. In trials, phones in Wellington have received warnings up to 20 seconds before strong shaking from distant quakes. That short pause can let train drivers brake, surgeons pause delicate operations, and school children dive under sturdy desks. To improve coverage, scientists plan to add ocean-bottom seismometers connected by fiber cables to the shore. Satellite links will serve remote hills where cellular towers are scarce. Machine learning tools are also being trained to sift live data streams for unusual patterns, cutting false alarms. Another breakthrough involves using fiber optic cables already lying on the seafloor as giant sensors. Tiny stretches in the glass strands created by passing seismic waves can be converted into digital signals, effectively turning internet lines into thousands of motion detectors. This method could blanket the Puisager Trench with coverage at a fraction of the cost of standalone instruments. As technology grows, the gap between detection and warning will shrink further, giving people the few heartbeats they need to act. How to prepare. Personal preparedness starts at home. Secure tall furniture with brackets, place heavy items on low shelves, and install latches on cabinet doors. Store at least 3 days of water, about 9 liters per person, and non-perishable food. Keep a torch, radio, spare batteries, and copies of key documents in a grab bag near the exit. Discuss a family meeting point in case phones fail. For homeowners, strengthening work like foundation bolts and plywood wall bracing can cost far less than post-quake repairs. If you rent, ask your landlord about safety upgrades and consider renter's insurance. Communities can map local resources: who has a chainsaw, who is a nurse, who can host neighbors if houses are unsafe. Schools should update emergency kits and practice drop, cover, hold at least twice a year. Businesses must plan how to keep staff safe and restart trade quickly, because paychecks matter for recovery. Pets need plans too. Keep a carrier, leash, and a small bag of feed ready. If evacuation centers do not allow animals, arrange a safe alternate shelter. Remember that aftershocks can continue for months. Refill supplies you use and keep the habit of checking expiry dates every daylight. Saving change. Community resilience. A megaquake will overwhelm even the best professional responders, so neighbors helping neighbors is vital. Community response groups can organize street-by-street phone trees and first aid workshops. In coastal towns, volunteer wardens may lead tsunami walks, marking the fastest uphill routes with bright paint. After the 2011 Christchurch quake, the Student Volunteer Army showed how quickly grassroots teams can clear silt and deliver supplies. Building these networks before disaster strikes builds trust, which in turn speeds recovery. Shared meals, local fairs, and cultural festivals also strengthen bonds that pay off in hard times. Simply knowing the names of the people next door can make the difference between isolation and support when the power's out and roads are closed. Cultural perspective. Maori tradition speaks of Ruamoko, the unborn child of Papatuanuku, whose movements cause earthquakes and volcanoes. These stories, passed through generations, place natural hazards inside a moral and spiritual frame. Events to respect, not fear. Incorporating this worldview into modern education makes preparedness messages resonate across cultures. On many marae, civil defense officers work alongside kaumatua to teach evacuation drills that blend scientific advice with ancestral wisdom. Songs, carvings, and storytelling evenings keep hazard knowledge alive in young minds. By valuing both science and tradition, New Zealand builds a more inclusive safety culture. Economic stakes. New Zealand's economy relies heavily on tourism, agriculture, and high-tech exports. A megaquake could close airports, damage hotels, and sever internet cables that carry cloud services overseas. Dairy plants need steady water and electricity. Without them, millions of liters of milk spoil. Vineyards in Marlborough may lose irrigation lines just when grapes need water. Insurance already costs more in high-risk zones, and another disaster will push premiums higher, possibly pricing some households out of cover. Rebuilding big cities diverts labor and materials from other projects, slowing growth. On the other hand, reconstruction can drive innovation, stimulating green building techniques and new infrastructure jobs. Planning that balance now will soften economic shock later. Creative industries, from film crews to game studios, also risk downtime if data centers lose power. Backup servers located in Wellington or Auckland may be offline just when overseas clients need content. Cloud mirroring across the Tasman Sea could keep projects alive and safeguard national reputation. Environmental aftermath. Large quakes can reshape ecosystems overnight. When slopes slide into rivers, they cloud the water with silt, harming fish like trout and inanga. Forest canopies stripped by slips expose soil to sun and wind, drying it out and inviting invasive weeds. Alpine lakes may suddenly drain if an outlet dam fails, stranding rare aquatic insects. In coastal zones, land can rise or drop a meter, turning wetlands to dry fields or drowning beaches. Scientists rush to map these shifts because they guide conservation efforts for decades. Restoring habitats fast not only protects wildlife, but also keeps water clean for towns downstream. Quakes can also trigger submarine landslides, stirring clouds of sediment that smother coral and sponge fields. These vibrant undersea gardens support commercial fisheries, so their loss has economic as well as ecological costs. Future research. To read the deep story of earthquakes, geologists drill into faults and sample the clay that forms during past ruptures. Chemical signals in those samples reveal temperatures and fluid pressures at the moment of slip. Offshore, autonomous submarines scan the trench slope, searching for fresh scars that show how far the seabed moved. Each new detail feeds international databases, supporting better hazard maps worldwide. Funding this research competes with everyday needs like schools and hospitals, yet the payback is massive when lives and billions of dollars hang in the balance. A bold proposal currently under review would drill a kilometer-deep borehole directly into the Alpine fault before it ruptures, installing high-pressure pore fluid gauges and ultra-sensitive microphones. If funded, this observatory could record the final buildup to a major quake in unprecedented detail, providing data to test models of fault weakening. Even if the experiment misses the next rupture, the instruments will continue to watch microslips that teach scientists how big quakes nucleate from small beginnings. Global lessons. Because tectonic plates ignore borders, knowledge must travel freely too. New Zealand learns from Japan's bullet train safety systems. Japan studies Kiwi advances in landslide mapping. Chile offers insights on rapid coastal evacuation, while California shares building code research. After a disaster, teams fly in to assist and to observe. Their reports fuel improvements back home. Social media now spreads those lessons faster than any academic journal, allowing families in Indonesia or Turkey to copy New Zealand's grab bag ideas in real time. Solidarity, not secrecy, turns hard experience into global resilience. A safer world begins with shared stories. Mental health after disaster. Earthquakes injure more than bodies. Sudden loss, noise, and uncertainty strain the mind. After Christchurch, many residents reported insomnia, flashbacks, and heightened anxiety at every minor tremor. Children clung to parents, and older adults feared entering multi-story buildings. Mental health teams set up mobile clinics in parks and offered free counseling. Community art projects, music events, and shared gardening plots later helped people process grief. Research shows that social support and clear information reduce long-term trauma. Therefore, disaster planning now includes psychological first aid training for teachers, police, and media workers. Knowing how to listen, reassure, and guide survivors is as crucial as clearing rubble. The March quake rattled shelves but spared lives, granting New Zealand a fortunate preview. The real test will come when a megaquake strikes one of the nation's great faults. Preparation is not about fear, it is about respect for the living planet. Secure your home, plan your exit, learn your local sirens, and connect with your neighbors today. When the ground shakes tomorrow, those simple steps may save you. Thank you for watching, stay safe, and we will see you in the next video.
One of the things I find most striking is the presence of Antarctica on ancient maps, because we didn't discover it until 1820.
Imagine waking up tomorrow and discovering that almost everything you were taught about the past was only half the story. Picture the textbooks closing like ancient doors, their facts replaced by deeper mysteries waiting to be explored. That dizzy feeling of stepping into the unknown is where journalist explorer Graham Hancock loves to take us. In this video, we will travel through the 9 bold theories that made him famous, angry, admired, and endlessly debated. Some call his work dangerous speculation, others hail him as a modern-day Indiana Jones. But no one can deny that his questions light a fire under the comfortable armchair of history. Our journey will move from hidden cities under Antarctic ice to glowing spirit creatures painted on cave walls, from secret geometry carved into pyramids to a golden chest said to crackle with divine power. Each stop invites the same daring question. Could advanced knowledge have risen and fallen long before the civilizations we celebrate today? And if that happened, what clues did the survivors leave behind for us to follow? Take a deep breath, open your mind, and keep your skepticism handy. The road ahead winds through forbidden history, cosmic disasters, and possibilities as vast as the stars. While experts debate his footnotes, millions of readers devour Hancock's books because they speak to a gut-level itch. The suspicion that our ancestors were smarter, braver, and more connected than we imagine. This script does not try to prove Hancock right or wrong. Instead, it lays out his storytelling path so you can judge the evidence for yourself over the next half hour. Ready? Let's dive in. Deep inside prehistoric caves in Europe, Africa, and Australia, ancient artists painted half-human, half-animal beings, known as therianthropes. Most archaeologists see creative myth or shamanic vision. Hancock sees something further: records of real encounters. He argues that hunters chewing hallucinogenic plants entered altered states in which otherworldly teachers stepped forward, sharing tools, symbols, maybe even directions about the cosmos. The strange figures became snapshots of those meetings preserved in mineral pigments. If that sounds wild, Hancock agrees, yet he points out how similar the pictures are across continents and millennia. Antlers sprout from human heads in France, serpent limbs writhe in South Africa, birdmen dance in Australia. How did isolated tribes imagine the same hybrids unless they met the same visitors? For Hancock, the simplest answer is contact with intelligent entities that exist beyond ordinary sight. Whether they travel on interstellar craft or emerge from inner dimensions is open, but the message stays consistent. Someone or something reached out to humankind long ago. Hancock also reminds us that modern volunteers given the same mind-altering plants often report glowing beings who speak in symbols. The overlap between present testimony and ancient art pulls the timeline tight, suggesting a repeated pattern of contact. Instead of dismissing the images as drug dreams, he asks us to consider them as minutes of the first interspecies conference, sketched quickly before the fire went out. Skeptical researchers counter that similar brain chemistry can produce similar visions, yet Hancock nudges them to run with that idea. If the mind is a receiver, maybe those chemicals open the same channel, the way any radio tuned to 101.3 FM will catch the identical song. That thought alone, brains as antennas rather than generators, turns the usual picture of consciousness upside down and sets the stage for deeper questions about where creativity truly begins. Roughly 12,800 years ago, at the edge of the last ice age, Earth staggered into sudden cold. This jolt, called the Younger Dryas, froze forests, starved megafauna, and pushed human groups back to survival basics. Hancock believes the trigger was a comet that shattered in the atmosphere and rained fire across the planet. In Magicians of the Gods, he gathers melted glass, crater fields, and ancient legends of burning skies as clues to a single disaster. The idea is more than climate science, it is cultural. Hancock suggests that an unknown advanced civilization thriving before the comet was almost wiped out. Survivors scattered, carrying fragments of lost knowledge. Think of black-clad librarians racing from a burning library, clutching a few rescued scrolls. Those scrolls became seeds of future cultures, germinating whenever peace returned. He connects this story to flood myths that pop up on every continent. Aboriginal tales of the rainbow serpent, Babylonian epics of Gilgamesh, and the biblical story of Noah echo the same pattern. Fire in the sky followed by deluge below. For Hancock, those overlapping memories are not coincidence, but eyewitness reports whispered across generations. If even half of them are accurate, the comet event was a true global reset, knocking human progress back to the Stone Age and burying earlier achievements under layers of ash. To strengthen the case, he highlights nanodiamonds and platinum spikes found in a black matte layer across North America and the Middle East. These markers, formed only under extreme heat and pressure, fall precisely at the younger Dryas boundary. Critics argue for local fires. Hancock counters with global distribution. The debate is fierce, yet every new drill core becomes another coin tossed on the scale, tipping it slowly toward or away from a planet-wide cataclysm. Enter a frozen world at the bottom of the map. Under 3 kilometers of ice, Hancock imagines the marble pillars of a forgotten metropolis, Atlantis. He builds this picture on a controversial geological idea known as crustal displacement. If Earth's outer shell can slide over its molten sublayers, continents might shift latitude in a geological instant. Under this scenario, a warm, habitable Antarctica could have slipped south 12,000 years ago, suddenly flash freezing any society that lived there. Supporting clues come from the 1513 Piri Reis map, drawn with data older than European exploration. It seems to show ice-free Antarctic coastlines with uncanny accuracy. Who mapped them? Hancock asks. If not an earlier seafaring culture? Add in legends of a drowned golden age from Egypt to Mesopotamia, and the icy silence of the South starts to sound like history's vault. Skeptics point out that cores drilled through Antarctic ice record millions of frozen years, but Hancock counters that only parts of the continent are sampled and rapid crustal shifts could create mixed signals. He calls for more open-minded surveys using ground-penetrating radar. If they reveal buried walls or carved columns, the debate changes overnight. Until then, the possibility lingers like warm breath in polar air. What if the real Atlantis sleeps below our coldest desert? If satellite radar were to detect symmetrical ruins beneath the ice, modern politics would ignite as fiercely as any ancient volcano. Who owns the heritage of a continent without citizens? Hancock uses that thought experiment to show how revolutionary discoveries can ripple through law, identity, and even spiritual belief, reminding us that history is not just about the past, it is power in the present. Turn toward the Giza Plateau and stand before the Great Pyramid. Its blocks fit tighter than a credit card, its base aligns almost perfectly with true north, and its descending passage aims at the exact pole star of the era. For mainstream Egyptology, these feats reflect brilliant engineering around 2600 BC. Hancock says the date and the builders are wrong. He argues that the pyramid encodes constants of the planet, from the length of the solar year to the speed of light measured in meters per second. Such precision, he insists, implies lost science. The structure's placement also mirrors Orion's belt when plotted against the Nile as the Milky Way, hinting at a master plan drawn thousands of years earlier when those stars sat lower in the sky. In this view, the Fourth Dynasty merely inherited a monument they could neither replicate nor fully understand, turning it into a king's tomb as an afterthought. Hancock's critics say there is no inscription proving older origins. He counters that an absence of graffiti is hardly proof of absence, especially if the builders respected the site enough to leave it unmarked. Meanwhile, erosion patterns at the pyramid's base may hint at wetter conditions earlier than dynasty timelines allow. These little cracks in consensus form the ladders Hancock climbs, searching for an age when pyramid stones were freshly cut prototypes of a science we have forgotten. Another clue he raises is the internal shafts aimed at specific star groups, perhaps to guide the pharaoh's soul or someone else's spirit toward the heavens. The mechanics of those narrow passages, sealed by swivel doors, hint at ritual precision too elaborate to be mere tomb decoration. Hancock suspects the pyramid doubled as a machine for initiations, a resonant chamber where sound and geometry lifted consciousness the same way cave art lifted hunters into spirit realms. Plato spoke of a mighty island empire that vanished in a single terrible day and night. Most scholars file that story under allegory. Hancock thinks differently. He sees Atlantis not just as Antarctica, but as a network of coastal cities wiped out by post-Ice Age floods around 9,600 BC. When sea levels surged over 100 meters, technology centers along the old shores drowned. Refugees retreated upriver, founding new settlements that rose mysteriously fast. Places like Sumer, ancient Egypt, and the Olmec heartland. In this scenario, the sudden appearance of astronomy, geometry, and monumental architecture is no miracle. It is inherited memory. Step pyramids in Mexico and ziggurats in Iraq echo a shared blueprint, carried by voyagers who spoke in symbols rather than common tongue. Hancock likens their role to teachers planting gardens. They showed indigenous societies how to read the heavens, track calendars, and build in stone, then step back into legend. Stories of civilizers arriving after floods reinforce his claim. The Andean Viracocha, the Maya Itzamna, and the Egyptian Thoth all fit the pattern. Bearded strangers teaching math and writing, then sailing away. Whether these figures were literal refugees or mythic masks for earlier knowledge, Hancock sees them as sparks thrown from a single dying fire. Follow the sparks, he says, and you trace the outline of a civilization big enough to light the ancient world. He also cites genetic studies showing sudden diversity bursts in post-Ice Age populations, proposing that refugee mingling could explain those patterns. While scientists prefer migration models, Hancock suggests we compare DNA timelines directly with flood dates to see whether legends and lab work line up better than we think. The next leap is even larger. If prehistoric wisdom seems to arrive from nowhere, perhaps it literally came from somewhere else. Hancock explores this in Supernatural, combining mythology with modern reports of altered state visions. He notes that tribal shamans, medieval mystics, and 20th century UFO witnesses all describe luminous beings who deliver messages about Earth's destiny. The overlap, he argues, points to a cross-dimensional meeting place where consciousness itself is the vehicle. Rather than silver saucers landing on the White House lawn, Hancock imagines contact carried through mind and myth. Sacred plants might tune human perception to frequencies where advanced intelligences operate. Those intelligences could nudge culture forward when conditions are right, the way gardeners water seedlings. Whether we label them spirits, angels, or aliens, he contends, their fingerprints may cover surprising chapters of our story. Skeptical, Hancock invites comparison. Why do distant tribes share star maps that match telescopic accuracy? Why do visionaries isolated by centuries sketch the same spinning wheels and tall, shining figures? Until those coincidences are fully mapped, he argues, the door to extraordinary influence remains ajar. Close it too quickly, and you might miss the guest who has been knocking since the Ice Age. Latest quantum theories that treat information as fundamental give Hancock new vocabulary. If reality itself is data, perhaps intelligent data structures, call them cosmic software, interact with organic hardware like us. The speculation is bold, but it reframes ancient visions as potential crosstalk between different layers of the same universe, rather than miracles or hallucinations. From cosmic gardens to biblical legend, the Ark of the Covenant, built to house the Ten Commandments, it supposedly shot bolts of fire, toppled city walls, and killed the unworthy who touched it. Officially lost after Jerusalem fell in 587 BC, the Ark disappears from standard history. Hancock's detective work leads to Ethiopia, where Orthodox monks in Axum insist the relic still rests in a small chapel, guarded by one chosen priest. No outsider has verified the claim, yet Hancock goes further. He proposes that the Ark's gold-plated cedar and twin cherubim form an electrical capacitor able to store and discharge energy, a piece of high technology misunderstood as divine wrath. Imagine a portable power source carried into battle by desert nomads, its crackling arc mistaken for God's voice. The idea may sound like science fiction, but Hancock points to laboratory replicas that generate measurable voltage. He also notes that early Jewish texts warned Levites to wear special insulating clothing and use carrying poles, sensible precautions if high voltage were involved. Whether or not the Axum Chapel houses the original, Hancock argues that the Ark legend records a moment when spiritual symbolism and practical engineering were one and the same. He dreams aloud of a transparent vault where impartial engineers could scan the artifact without violating faith. Until such diplomacy emerges, the Ark remains both a religious cornerstone and a technological cliffhanger. its true nature sealed by doorkeepers who trust tradition more than peer review. Walk a finger along the spiral of a nautilus shell, then along the curves of a temple staircase, and you meet the same ratio, phi, the golden mean. Hancock believes ancient builders embedded such mathematics intentionally to resonate with cosmic order. Known as sacred geometry, these patterns appear in Stonehenge, Angkor Wat, and the Navajo sand mandala. Alignments with solstices, lunar standstills, and horizon points suggest that stone circles and pyramids were more than shelters. They were tuning forks for the human spirit. By standing inside these harmonically proportioned spaces, participants might have entered altered awareness, feeling unity with the sky. Hancock argues that this design tradition hints once again at shared ancestry. If diverse cultures receive identical geometric software, perhaps a single older civilization or a cadre of traveling sages distributed the code, inviting humanity to join a larger orchestra. Recent scans at Göbekli Tepe in Turkey, dated to 9,600 BC, reveal geometric precision equal to later cathedrals. The discovery pushes organized architecture thousands of years earlier than believed. For Hancock, every new dig extends the shadow of lost mastery deeper into the past, urging researchers to follow the pattern rather than the calendar. Mathematical historian Keith Critchlow once told Hancock that sacred builders saw number as a living substance, not an abstract count. In their view, 3 upheld stability, 4 described matter, and 5 bridged the earthly and the divine. When those numbers arrange stones and angles, they invite people to walk physically through an equation, a concept that modern classrooms rarely mention, but ancient architects may have taken for granted. Guarding the Giza Plateau, the Sphinx stares east as the sun rises. Conventional dating connects it to Pharaoh Khafre around 2500 BC. Hancock, collaborating with engineer Robert Bauval and geologist Robert Schoch, points to rainfall erosion on the limestone body, where that would require millennia of heavy storms last seen at the end of the Ice Age. He also notes that the lion-bodied statue aligns with the constellation Leo at dawn circa 10,500 BC, when Orion's belt matched the pyramid layout exactly. If the Sphinx is truly that old, the rewriting of history is enormous. Egypt would not be the origin of monumental stonework, but its inheritor. The Sphinx becomes a silent messenger from an earlier epoch, gazing toward a celestial marker that told its builders, "This is the age you live in. Remember us." Hancock suggests a ritual purpose. The monument was both clock and compass, anchoring sky time to ground space so future generations could rediscover the lost calendar. Critics reply that erosion could be caused by wind and sand, yet the depth and rounded channels resemble water wear more than desert abrasion. Until a definitive core sample settles the debate, Hancock believes the giant cat continues to ask a question with its stony stare. How far back does the story of civilization really stretch? He adds a possibility that the Sphinx's head was recarved from a larger lion, suggesting multiple renovation phases spanning thousands of years. If true, the statue is not a snapshot, but a palimpsest. Each chisel marks another chapter in a story still unfolding beneath Egypt's relentless sun. So where does all this leave us? Some viewers may be ready to toss every classroom timeline into the compost heap. Others may feel their eyebrows reaching permanent orbit. Hancock himself encourages neither blind belief nor reflex dismissal. His challenge is simple: investigate with curiosity. Dig, measure, and question until the evidence speaks louder than tradition. Whether or not Atlantean engineers carved the pyramids or spirit teachers sketched therianthropes, the real treasure is the habit of wonder. Our planet carries scars of cataclysm, whispers of forgotten stars, and monuments that still refuse easy answers. If Hancock's stories push more minds to pick up a trowel, aim a telescope, or open an ancient text, then the quest has already begun. Even if future digs disprove half these notions, the exercise teaches resilience of thought. True knowledge grows when certainty shrinks. Thanks for exploring with us today. If you enjoyed this tour through forbidden history, smash the like button, subscribe for more journeys beyond the map, and ring the bell so you never miss an episode. New adventures are always on the horizon, And if all of this seems overwhelming, take heart. The very act of listening, of daring to imagine deep time, connects you to an unbroken chain of storytellers stretching back to the first campfire. See you in the next video.
For decades, people living on the West Coast have been warned about an earthquake so strong it could produce a tsunami the size of a 10-story building.
Beneath the calm blue skin of the Indian Ocean lies a restless creature. It is huge, silent, and older than any city on Earth. Yet most people have never heard its name. Geologists call it the Sunda megathrust. Think of two giant slabs of rock, each as wide as countries, slowly grinding against each other in a contest that never ends. One slab, the Indo-Australian plate, dives under the lighter Sunda plate. Every minute, the heavier plate slips only a hair's breadth, but that tiny push keeps adding strain to a hidden spring. We start our story here because what happens below this water matters to all of us. In December 2004, the spring snapped. A 9.1 megathrust earthquake unzipped more than 1,200 kilometers of fault in seconds. Whole blocks of seabed leapt upward by 6 to 20 meters. The movement shoved billions of tons of water out of the way, and that water became a wall racing toward the coast. By the time the ocean calmed again, more than 230,000 people were gone. Houses, schools, and memories washed away in an afternoon. But the 2004 rupture was only one tear in a giant seam. Great sections of the Sunda megathrust remain locked, storing even more strain than the piece that broke 20 years ago. Today, we explore how this fault works, why it kills, and what might happen when it breaks again. Quiet surface, hidden power. If you sail off Sumatra or Java on a clear morning, you might see fishermen casting nets, surfers waiting for a perfect wave, and children laughing on the beach. Nothing suggests danger. The sea smells of salt and coconut smoke. Yet kilometers below, rock is bending like a loaded bow. Because it is rock, not wood, the bend builds slowly. Instruments on the seafloor record millimeters of warping each year, too small for people to feel. Satellites see the islands creeping westward, dragged by the stuck plates. This mismatch between calm surface and violent depth is the heart of the problem. People judge risk by what they notice, and most days offer no hint. Buildings grow taller, ports busier, tourists flock to Bali, and the memory of 2004 fades. But physics does not forget. Stress keeps piling up where the two plates grip. When friction finally loses its grip, the locked patch will shoot forward, releasing decades or even centuries of pent-up energy in less than a minute. The bigger the locked patch, the bigger the quake. Tour guides point out coral reefs glowing like stained glass, and couples pose for sunset selfies. Investors study seaside plots, seeing only profit. The very beauty of these shores acts like a lullaby, convincing residents that tomorrow will look like today. In many villages, people have names for local winds and fishing currents, but no word for tsunami because the last one struck before their grandparents were born. Without living memory, risk becomes an abstract rumor. That mental blind spot is as dangerous as any wave, because a person who cannot imagine a wave cannot run from it. Geological setting. The Sunda megathrust stretches for more than 5,500 kilometers, from Myanmar's Andaman Islands down past Sumatra, across the length of Java, and toward the eastern chain of the Lesser Sunda Islands. It marks the boundary where the oceanic crust of the Indo-Australian plate dives, or subducts, beneath the crust of Southeast Asia. The plates converge at about 5 to 7 centimeters a year. The speed fingernails grow. Over a human lifetime, that seems tiny, but multiplied by centuries, it bends mountains. Under the sea, the subduction interface is not smooth. Ridges, trenches, and piles of sediment create bumps and hollows. Some sections creep continuously, sliding without big quakes. Other sections are locked, held firm by friction. Lock zones are the ones we fear, because only they can store the elastic strain needed for a megaquake. Each segment has its own history of breaking. Scientists map them by dating coral that got lifted in ancient events, by drilling into the fault, and by reading GPS data taken from tiny steel monuments bolted to bedrock. Indonesia's western coastline sits right on top of this boundary. Cities such as Padang, Bengkulu, and Cilacap are less than 200 kilometers from the trench axis. Jakarta, though farther inland, is still close enough that a big rupture could rattle skyscrapers and send a tsunami through its outer islands. Java alone holds more than 140 million people. That means the Sunda megathrust is not only long, but also runs beside one of the most crowded coastlines on the planet. How subduction quakes make monsters. Once formed, a tsunami radiates outward in rings. Computers predict arrival times by solving wave equations on a sphere. But in reality, the seafloor's bumps bend and focus energy like a hand lens bends light. Undersea ridges can steer waves, making some distant coasts take harder hits than nearer ones. For the Indian Ocean, Sri Lanka's east and India's southeast are often in the line of fire. The Maldives, though low-lying, sometimes see weaker crests because deep channels scatter energy. East-facing beaches of South Africa can feel pulses that traveled 9,000 kilometers. Even inside Indonesia, bays become traps. In Aceh, Lokanga Bay amplified the 2004 wave to 30 meters. Researchers now survey every inlet, mapping whether it will funnel or deflect future surges. Warning time depends on distance. People in Jakarta might have an hour. People on the Mentawai Islands would have minutes. The difference between life and death may be as small as recognizing the roar of receding water or following a teacher's drill without hesitation. In tsunami safety, awareness is the cheapest and strongest defense. Human and economic stakes. Indonesia is Southeast Asia's largest economy, the world's fourth most populous nation, and a hub for shipping lanes that carry oil, gas, and electronics. A megaquake on the Sunda megathrust would not only wreck homes, it could choke ports, break fiber optic cables, snap power lines, and close airports just when aid must arrive. Factories from Medan to Surabaya feed global supply chains with palm oil, rubber, textiles, and microchips. A month-long shutdown would ripple through world markets. There is also the social fabric. Coastal regions depend on fishing and tourism. A devastating tsunami would push families inland, crowding cities that already strain to provide housing and jobs. Memories of disaster can last generations, shaping where people choose to live and invest. Insurance models suggest a repeat of 2004 in today's economy could cost insurers more than $50 billion, testing the reinsurance sector. Healthcare would face double pressure, trauma cases at first, then waterborne disease in crowded shelters. Psychological scars could linger for years. Schools destroyed in Aceh took nearly a decade to rebuild fully. When we weigh hazard, we must add these hidden costs, not just the ruined buildings. Protecting critical infrastructure now, hospitals, data centers, fuel depots, is cheaper than rebuilding after salt water and shaking turned them to rubble. Cultural loss is harder to price. Temples, mosques, and coastal forts hold archives, relics, and ancestral graves. When salt water crushes a centuries-old carving or floods a burial ground, part of collective identity dies. Artists, fishers, and tour guides may lose both tools and customers at once. The long tail of disaster includes depression, migration, and the fading of songs sung only in seaside dialects. Early warning and preparedness. Since 2004, Indonesia has installed more than 150 broadband seismometers, 60 tide gauges, and dozens of GPS buoys. Data flow to a central center in Jakarta, where algorithms estimate tsunami risk within 2 to 3 minutes. Sirens, text blasts, and social media posts follow. The system saves lives during smaller quakes, yet gaps remain. Many buoys break loose or are stolen. Mobile networks fail when power goes out, and most rural villages still lack tall shelters. Community drills are the strongest link. In West Sumatra, some schools practice evacuation twice a year. Students learn to count 1 elephant, 2 elephant, until shaking stops, then run along marked paths to a mosque on a hill. Studies show children who drill are more likely to guide others. Simple signs, arrows, and blue wave logos now line roads pointing to safe ground. Education turns abstract science into muscle memory. Engineers push for vertical evacuation towers, tall concrete platforms strong enough to survive waves. Japan's design codes offer templates, but funding is limited. Meanwhile, researchers deploy ocean bottom fiber cables that can detect pressure changes in seconds, promising faster alerts. Technology and training must advance together. A sophisticated alarm is worthless if people ignore it, and perfect discipline means little without a signal. Bridging that gap is the next frontier of tsunami safety, building resilience together. Megaquakes are natural, but disasters are partly human. The shaking cannot be stopped, yet the death toll can. That idea guides resilience work across Indonesia and the rest of the Indian Ocean rim. It starts with land use planning. Coastal zones that sit lower than 10 meters above sea level face the highest tsunami risk. Mapping those zones allows officials to zone for parks, warehouses, and rice paddies instead of dense housing. When the worst happens, fewer people stand in harm's way. Next comes construction. Simple changes save lives. Tie beams that strap walls together, lighter roofs that will not crush occupants, flexible foundations that ride out shaking, and breakaway walls on ground floors that let water flow through. None of these ideas requires high technology, only training and small extra cost. Microfinance groups now offer low-interest loans for quake-safe retrofits. In cities such as Padang, discount permit fees for builders who meet new standards. Early education shapes culture. Children who grow up practicing drop, cover, and hold on carry that reflex into adulthood. Storytelling matters too. Museums in Aceh host survivor testimonials, turning memory into a living warning. Annual commemoration days blend prayer with drills, reminding even those born long after 2004 why the sirens exist. International partnerships provide tools. The United States, Japan, and Australia fund satellite relays, supercomputers, and training workshops. In return, they gain better global models and a more stable trade partner. Resilience is not charity, it is shared security. Finally, personal preparedness closes the circle. A family evacuation plan, a whistle, a waterproof pouch for documents, and knowledge of the nearest hill can tip the odds. One household seems small, yet millions of small choices add up to a national defense stronger than concrete walls. Nature writes the first line of the story, but people choose the ending. Thank you for watching. If this story moved you, share it with someone who lives near the coast and talk together about where you would run if the water ever pulls back. Knowledge spreads faster than any wave, and those few seconds of awareness can draw the line between tragedy and survival. Subscribe for more simple science stories, and until next time, keep one eye on the horizon and stay curious.